Hi everyone. Karen, I have a question for you. I did my PhD on metakaolin limestone blended cement, and we use kaolin from Georgia. And when we increase the kaolin content up to 20-30% by mass, the biggest challenge we faced was the workability. And I tried different admixture, we did different studies, but then we have to use higher amount of admixture, and then there was a cost associated with that. So I would like to get your opinion of how do you think we can overcome that challenge? Thank you.
Well, the big thing is don't use metakaolin. First and foremost, it's very expensive. It's about 3 times the price of cement, so it makes no sense at all. And so with calcined clays, you've typically maybe got 40% kaolin. So you've got 40% of the stuff that's causing some workability issues. But then you add the limestone. And that's another very important thing about this synergy, that generally, if you're producing it right, the limestone can improve your workability. So that's basically the answer. Then you've got to, optimize your formulation according to your local materials. But I mean, we've taken this material in India, for example, to people making concrete by the side of the road. They're not going to use admixtures, and they can use it exactly the same with no admixtures. Now, in more high-tech applications, yes, you will need admixtures, but admixtures should be part of all good concrete, because that's the way you can minimize cement content. And there, it depends very much on your raw materials. The demand can be somewhat higher, but not necessarily hugely higher. And most of the admixture companies now have new products coming on the market that work very well with calcined clays. So the answer is, this is not the same as adding metakaolin as a binary component. There's lots and lots of differences, which mean that, as I said, we've used it in places with very low tech mixing, produce very good quality concrete with no significant admixture demand. Yeah.
Hi, I'm Julia from Meta. Thanks for the very nice presentation. Really good to see a really diverse set of solutions being shown, LC3, concrete AI, and carbon built. Are they complementary, and can they be compared quantitatively?
This is a difficult question to answer. I mean, the big advantage about calcined clays is you can use them in existing production. You can use them very fast. So, and you can introduce them anywhere in the world because the technology is already there. The problem with, I'm going to let Gaurav answer this question, but, I think you're talking about a time of application. You can't apply these electrolysis-based solutions today. And you can't, everybody's talking about electrolysis as being the wonder solution for a lot of different technologies, green hydrogen, everything like that. If you want to buy an industrial scale electrolyzer today, the waiting time is generally about 3 years. To produce 1 gigawatt of energy by electrolysis, you need 0.5 ton of iridium. The world production of iridium is 4 tons per year. So I think you see there the problems for implementing these kind of other technologies in the short term. And the short term is what matters.
Sure. So slightly different perspective to this. Couple of things. So concrete AI is fundamentally compatible with just about anything because it's agnostic to what the binder is made of. It's a pure optimization play. And so since it's a pure optimization play, you're agnostic to what's in it, so to speak. Okay, so that's number one. So do you have a comparative basis of assessment? The answer is yes, because you can effectively reduce everything into 3 metrics, one around cost, one around equivalence of performance, one around carbon footprint, and you've got an equal basis of looking at just about anything you get. Carbon built, totally different concept, based around masonry and precast particularly. That being the case, is based on a different manufacturing paradigm where you've got a whole lot more ability to control the process. Now, taking a step back and coming to things like electrolysis, I think Karen's spot on. I don't see anyone building an electrolysis plant overnight. But the question is, what's your time horizon? If your time horizon is a decade, I think the answer is yes. You'll see it happen for sure. Are you going to see it happen at the scale of the industry? Definitely not. You will see industrial scale plants coming online, but that's important because that's how you build confidence for transitions. Now, the comment around iridium is important, but I will also say that there's a vast range of electrolyzers that do not use PGM, so to speak, platinum group metals. And that's actually really quite important because, in fact, if you need to rely on PGMs, we will never achieve electrolysis at industrial scale. And so, in fact, a big part around, I think, what electrolysis is going to need is not simply platinum group metals, but really industrial capacity to go build electrolyzers. And I think that's going to be just as hard as the fundamental materials that you need to produce electrolyzers.
My name is Michael. The question that I've got is, I hear a lot about we're trying to go towards this goal of reduction of CO2. I don't hear a lot about this is the benchmark where we're saying that our efforts are starting and it pertains to NU as a whole. As to year by year, these are the efforts that we continue to improve on, but this is where we started. Because if not, what I foresee happening in legislation is they're going to go every year, oh, now you have a new benchmark, oh, now you have a new benchmark, and it's not seeing the compound effort that the industry is doing. What is that benchmark that has been agreed upon?
So I can offer one perspective to this. So you can look at SB 596, which is California's approach at cement decarbonization. It's benchmarked to when the bill came out, which was, I think, 2021 maybe, or 2022. It uses that as a reference basis going out to 2030 and then going out to 2045. So that's how you can set a benchmark. Now, that being the case, you can also use internal benchmarks. So as a company, you can use a benchmark to say, our original clinker factor was X, our specific intensity was Y, and we can use our own internal benchmarks to determine what the reduction looks like. You can zoom out and take the macroscopic view, which is, okay, by 2050, we need to be at zero, and in fact, taking out between 5 and 10 gigatons from the atmosphere. That sets the benchmark compared to today, which is at 40 gigatons of emissions to about 10 gigatons negative. So you've got about a 50 gigaton delta in that, right? So you've got a variety of ways that you could arrive at the benchmark. I think, to be clear, the benchmark is not that straightforward. Here's the reason why. Per capita emissions are very different on a country-to-country basis. They are also different on a jurisdiction-to-jurisdiction basis, and even at a subnational level. So the question that really comes about is, do you do it by sector? Do you do it by jurisdiction? Do you do it based upon economics, aka per capita basis? I'm not sure that there's a clear answer to it. One way to do it is do it for a single sector at a single time in a single place.
Any other comments? Thank you very much. I'm Johan Silverbrand from Sweden. I think very nice and interesting presentations. I have one comment first. I don't think it is a problem that the price of cement will be twice as high if you are working with CCS, because you don't need more than 50% in most places. You are using too much cement, and it is because it is too cheap, I think. And but in Sweden, we are planning to open our largest cement factory for CCS in 2030, and in Norway they are earlier, in 2025, I think so. But these are, I guess, 2 out of 2,000 cement factories in the world. So it is a long run, and of course CCU is better than CCS. But when are you going to have a CCU of the same scale as a cement factory?
Well, if I can comment first of all on the cost of price, I think for just about everybody in this room, what you say is absolutely true. That cement is way too cheap, and we could afford to pay much more of it. But you have to take into account the real demand is the 1 billion people in the world who will live in slums. Mm-hmm. And the truth of the minute is, in Africa, the absolute price of cement is already 3 times what we pay in the US and Europe. And then when you translate that into earning power, it means you and me probably have to work 5 or 6 hours to buy a bag of cement. Somebody in Africa probably has to work 6 months to buy the bag of cement. So think where the demand is and where we need to address the problem. So yes, as I think you outline, in the developed world, CCS will come into play and the prices will go up. But when you consider that 90% of cement is already used not in those countries, you have to think of other solutions.
I can try and take a stab at the CCU comment that you made. I think to do utilization at the scale of emissions from a typical cement plant, so let's say 1 million tons of cement production, 700,000 tons of emissions, super hard, super hard. There's very, very few outlets for that much product that's based around carbon dioxide. And so there's quite a bit of work that's been done, and I think there's actually a new National Academies Committee that's actually looking at some of these things. But very hard, incredibly hard. There's a huge scale incompatibility.
Hello, this is Mohammed. My question would be to Dr. Gaurav. In one of your slides, it was mentioning that like carbonization of the waste-based minerals and natural minerals. So considering the decrease in amount of the available industrial byproducts, so the evaluation of this kind of materials in carbonization to obtain like magnesium or calcium carbonates is a promising or a long-term solution, like as most of them already has been used in cement production.
So I think I'm not sure I understand every part of the question, but I can try and respond to at least pieces of it. So I think it's definitely true that if you look at classic industrial waste, things like slags and fly ashes, globally speaking, there's not enough available. So doing carbonation with this is not a climate strategy by any means. Comment number one. Comment number two, if you look at the absolute abundance of minerals that contain things like calcium that could be used to produce cement, there's more than enough available, including beyond limestone. So if you just look at where the largest reservoirs of calcium are, it's actually not in limestone, it's actually in other stuff, and that's an important thing. So there's definitely enough calcium around. The question is, how do you get access to it? That's really the key question to ask. So it's not a question of capacity, it's a question of accessibility.
Thank you.
If I could just add to that, I think what you've also got to think about, if you're taking calcium out of rocks where the concentration is, say, like 10 to 20%, what are you going to do with the rest of the 80% of stuff you get left over? You know? So you've got, one, the problem of costs of these new processes, and two, the problem of the waste streams they will produce. You've also got to think, you know, we're mining stuff out of the earth. If you've got a concentration of, you know, 10% rather than in limestone very high, you're going to have to be extracting much bigger quantities. You know, so all of these things have to be taken into account. And I think it's going to be a very hard job to find other sources that make sense. But, you know, that does leave us with the fact that we will have to implement this carbon capture and storage. I don't talk about utilization because I think it's, you know, a little bit of a fantasy on the scale we're talking about. You know, there are ways you can store. There is big capacity for storage. And you have to say, well, you know, is the cost for doing all that more or less than the cost of extracting from other rocks and then dealing with all the waste they produce? It's a question of, you know, swings and roundabouts.
Very good. While we have Dr. Nmai and Dr. Scrivener up here, I guess I have a question about the compatibility of traditional admixtures with LC3 mixes. Either one of you have any comments on that? I'm sure.
I'll defer to you.
Well, yeah, I mean, the really good news is that all the traditional admixtures work perfectly well for calcined clays. Generally, as has already been commented, you may have to use somewhat more, and that's why the admixture companies are working to make more efficient ones, and they're succeeding. So we've worked with both Sika and MBCC, so I'm not partisan. You know, we've seen very successful admixtures from both these companies, and I'm sure there's a lot more other companies out there. You know, many different ones are available. So I think there's really, in the long term, we're going to see good admixtures, and I really do want to emphasize that good admixtures are the key to low carbon concrete, even without SCMs. You know, the savings you can get from minimizing your cement content are huge.
Great.
Yeah, that's the question behind it.
Question.
Hi, this is Debolina. In this conference, I heard a lot from Dr. Karen, and there's a lot of talk about the main demand of concrete and cement in Africa and Asia. But when we're talking about the solutions, a lot of these techniques are mainly applied in Europe and America, and all this legislation also. So this is more of a, I'm curious, how much interest are you getting from Africa and Asia about carbon capture or low carbon concrete? Or, yeah.
Yeah. Well, I mean, the short answer is we're getting a lot of interest from the cement companies who are producing there. And, you know, this is where I'm now concentrating my efforts, because I think we need to act where the demand is starting. You know, everybody talks about China having used more cement in 3 years than the US did in the whole of the century. That's all been done. That CO2 is already in those buildings or whatever. So we have to, and we have to work with these people. I think it's a very complex issue because we have to build capacity. I mean, this is what I'm now really working on. We're creating at EPFL a Center for Worldwide Sustainable Construction, and the idea is really there to partner with these companies to bring people to do research together and to see how we can implement in these countries. So for me personally, that's where I'm spending most of my time right now.
Thank you very much for very inspiring presentation. My name is Takafumi Noguchi from the University of Tokyo. As you know, the concrete is the second most consumed materials on Earth, and I think it has a potential to reduce carbon dioxide and also to capture the carbon dioxide from the air. So I am chairing the ISO standards committee, TC71 SC8. It is on the environmental management for concrete and concrete structures. We are currently trying to establish the qualifying method, how much carbon dioxide is reduced and also how much carbon dioxide is captured in the concrete. But I heard the United States is fading out from our community, ISO standardization. It is very sad for us. So we need a leadership, and I think you should come back to the ISO community because the ACI code is very important. Probably we have to challenge how to mitigate the carbon dioxide using the concrete. Okay, it's my comment, not question. Thank you very much.
Thank you.
Thank you. Obviously, we need to discuss that internally at ACI.
Exactly. and ACI did, if I can just comment on that, you know, ACI has representation. Staff members go to the committee meetings. What ACI did was not pulled away from being the hub and essentially funding the whole thing. Basically, yeah. But we're still involved.
Okay, question.
Hi, Ami from Ozinga in Ready Mix in Chicago. Excellent presentations. I really like that. I have a question for Karen. Hope you remember me. From our meeting in Chicago, I really forgot to ask you about this question. Maybe you studied that. Just for further clarification, you showed a lot of results, and I wonder, like, if the LC3s that you tested were from the blending, or you, because there are some overlaps for calcination of the limestone to get the clinker and also the calcine clay. I don't know if there are like synergies or like some overlaps, if you can calcine the product together for a better consistency, or the results are better or more consistent if you blend the different ingredients together?
Okay, the short answer is no. You know, like basically you have a most efficient process if you produce clinker on the one hand, which needs to go up to temperatures of 1450 to get the clinkering and the formation of the alite, and the calcined clay on the other. What's very important is to recognize that this C3S, this alite compound we form, is very efficient. You know, I mean, a lot of people talk about high B-lite cements, but they make no sense whatsoever because you have minimal CO2 savings, you have less calcium hydroxide for the pozzolanic reaction, so you lose out completely. In fact, if we could make cements with higher alite content, then we would be able to go to higher levels of substitution, and we would reduce CO2. So, you know, a lot of people have kind of played around. We're going back to the early days, in fact, of cement, where they actually did the calcination at lower temperatures, and you just get kind of a mess with even more heterogeneity. You know, I mean, heterogeneity is a big problem because then you have to have bigger safety margins. So, no, let's stick to making clinker on one hand. Maybe we can optimize that process and calcined clay on the other side.
Okay, I saw a question over here.
Yeah, my name is Don McNutt. I'm with the American Concrete Pipe Association. And you made a comment about we can afford to increase our cost or price of cement. Well, we have the plastic pipe industry that's trying to put us out of business. And price is very important in our industry. And I promote concrete pipe use throughout the country. And we would have a very difficult time with any price increases based on this type of scenario, which I understand what we're trying to do. I agree with it, but boy, price is everything.
Yeah, of course, price is everything. And I mean, you know, as I showed you, the advantage of LC3 is you could actually produce it more cheaply. So that will give you an advantage. But this is all comes down to CO2 taxes. When CO2 taxes are coming in, I think the plastic pipe industry is going to have a huge problem, because if you look at the CO2 intensity of polymers, it's like 10 to 20, 30 times that of concrete. So I understand your perspective. I think we just have to, but the point I was trying to make is that while we're all comparatively rich and well off, we could afford to pay more. Most places in the world, people can't afford to pay more. So I'm all for low prices, and that's why, as I say, LC3 is a very good technology because it can save you a lot of costs.
Hamid Sadati, thank you for the great presentations. A quick question for Dr. Sant. Very interesting concept, the net present value when we are comparing the carbon capture in an accelerated environment versus natural carbonation. Can you please offer any estimates on the equivalent natural carbonation duration that we should be expecting to have that break-even time when we are comparing to the accelerated environment?
So I think, there isn't a single answer to this, right? Because it depends upon the water cement ratio of the concrete, it depends upon its permeability, so there's no single answer to it. But if you choose to sort of average it, right? Exactly. And say, let's assume that all concretes produced in the world end up at a water cement ratio in some way of 0.51, right? That's not a true statement, but let's use that as a basis, right? And you say, I want to try and do an equivalence analysis around if I manage to take up X units of CO2 in 24 hours, how long does it take me to take up X units of CO2 in a natural carbonation process? Typically, it's on the order of 2 decades.
2 decades?
Yeah. Long time. And this is optimistic. The pessimistic scenario is actually quite a bit worse. The challenge is, this is a hard question to answer because there's huge uncertainties on what your actual diffusion coefficients look like.
Yeah. Right. But if I could make a further comment on that, I think what we forget about is that only roughly half cement is used in concrete. The other half is actually used in mortars. And mortars, because of the kind of way they're used, like renders on the outsides of houses or between bricks or making blocks, they generally carbonate a lot faster. So, you know, if you put a render on the outside of your building, it's a very porous material, it doesn't need to have any strength, it's probably going to carbonate in 5 years. And, we should think about our concretes as well. We talk about carbonation because we're worried about reinforcement corrosion. But, we can also think about replacing steel reinforcement with glass reinforced polymer. There was a good presentation on that on Sunday. And then maybe we would be interested to accelerate our carbonation.
Okay, I think we have time for one more question here.
Thank you. Areski from Sherbrooke University. I have a question for Charles. I like the presentation you did about the flow to go from starting and creating and do standardization for new materials, etc. I think there is one step there which we have to speak about, because you said standardization, then you said pilot projects and development of pilot projects, etc. I think before to do standardization, we have to go in this field test before.
Yeah, definitely.
So, but this is the problem. I can give you the example of the glass powder that we worked on. It took 18, 20 years to develop the standard.
Mm-hmm.
And imagine a small company developing a very good material, having to find finance to wait 20 years.
Mm-hmm.
So this is really the trick where we should work together to find how to activate the process, of course, with the protection of the populations.
Yeah.
So
no, I mean, your comment is exactly right, and again, that's why I said at the end, that new is actually, ACI new actually well suited, to be the catalyst, because the traditional ways of doing it, believe me, I live this day in and day out, and I'm also extremely active in ASTM, because we have to work through ASTM to develop, the specifications and the test methods and so on. And there are things that we're doing over there to also help to shorten, the time that it takes to develop, ASTM standards. So it's not just focused on ACI, also involves, ASTM standards. And incidentally, that's one of the reasons why we ended up having ICCES as an allied organization. Because the ACI 318 code, can be a barrier to introduction of, new technologies. A lot of engineers will not specify a new material if it's not in the code, And a way to get around that is by going through ICCES, And then once you get the ESR, the Evaluation Services Report, that can be given to code officials, and that allows you then to sort of bypass the code until such time that it gets into the code. Now, ICCES is also critical because if you don't have a standard specification or test method, those can be developed and be part of the ESR as an appendix until such time that ASTM develops, either the specification or the test method, and then they get dropped. So hopefully, that will give, you folks a sense of why the allied organizations are, critical, to the mission of NEW. Yeah. Thank you.
I want to thank our speakers. Excellent questions, excellent speakers. Big round of applause.